Let's talk about an overview of mixture problems. So the general principle for percentages is the whole amount times the percentage written as a decimal is the part amount. We see this, for instance, in like just percentages dealing with sales tax. So $10 sticker price on a hat, 6% tax. So the whole amount 10 here times a percentage as a decimal 0.06 is equal to the part amount 0.60. This is the amount of tax to pay. It ends up being 60 cents. The total to pay is $10 plus the tax. It's a plus because we have to pay this also. And I know this sounds strange, but how tax works is we pay even more than the whole amount. So I hope the whole amount phrase is not too confusing here. You actually pay the whole amount to the store, but then you pay even more than that, right? The store gets a little extra that they have to forward on to the government. That's the tax part. The same thing happens even if the original amount or the whole amount is not known, right? So if it's not a $10 sticker price, but an unknown sticker price labeled with an H, we still do the whole amount, H times the percentage, 0.06. That's the part amount. So 0.06 times H, that's the amount of tax to pay. Just like up here, here's the total amount to pay. Now this equation here, like a certain amount times the percentage as a decimal equals the part amount, written up here, happens also for mixtures or solutions or liquids. It's just kind of the labels of the pieces change. So the amount of liquid times the concentration, that's that percentage, is equal to the amount of acid. So 8, that's the amount of liquid, times 0.5, that's the concentration as a decimal, equals 4 here, that's the amount of acid. If we say this in words, a container has 8 liters of liquid and 50% is acid. So that means that 4 liters of the container is acid. And think about it, right? This is the 8 liters of stuff, of liquid. Some of the liquid is acid, some of the liquid is not. Let's just say that the non-acid part is water. So if there's 8 liters of liquid and half of it is acid, that means 4 liters is acid. By the way, this is not the only way you can have a concentration of 0.50 or a 50% concentration. You could have a container with 12 liters of liquid and 6 of those liters, half of it, is acid, or a container which is 14 liters of liquid and 7 of those liters, right, half, is acid, or if the container had 44 liters of liquid, then half of it, 22 of those liters, would be acid. I mean, there's so many examples of this. Now, what I want to ask about is this concentration being 0.5 we talked about, but what if this 0.5 is in the other spots? What about here in the amount liquid? What about if the 0.5 is here in the amount acid? So on the next slide, what does the amount of acid equals 0.5 means? So I'm talking about 0.5 if it were in this spot, right? So as examples of this is just trying to say that there's 0.5 liters of acid. So you could have a container, here's an example of it. You could have a container with 0.5 liters of acid and literally no water, 0 liters of water. Or 0.5 liters of acid and 0.2 liters of water, 0.5 liters of acid, 0.5 liters of water. Here it matches, right? The same amount of acid as there's water in that container. Another container, 0.5 liters of acid, 1 liter of water, 0.5 liters of acid, 18 liters of water, 0.5 liters of acid, 10,000 liters of water. That's way more water than acid. But in all of these 1, 2, 3, 4, 5, 6 situations, all of these different containers, if they just start with a certain amount of acid, 0.5 liters, and you can pour in no water or a lot of water or a little bit of water, these are all examples of amount of acid equals 0.5. Now, what about if we change and have the 0.5 written in this spot in the amount of liquid? This is the amount of liquid equals 0.5 means that the total amount of liquid, that's the acid liquid and the non-acid liquid, all combined is 0.5 liters. So we don't actually have a lot of room to play with this. And one example is container with 0.5 liters of acid and 0.00 liters of water. So no water, all acid. This plus this is 0.5 liters. You could have 0.4 liters of acid and 0.1 liters of water, so that when you add these together, the total amount of liquid is 0.5, right? This plus this is that. You could have 0.3 liters of acid, 0.2 liters of water. Here's another example, here's another example. You could have no acid at all and 0.5 liters of water. So when you combine it, there's no acid, add to all water, that's 0.5 liters of liquid. Just to check it, test it, what if you had so let's go to still this, 0.5 liters of liquid, 0.01 liters of acid. Can you think for a moment how much water there is? Should be 0.9, oop, that's a typo on my part, sorry. Can you just go, I was making the slides too fast, should be 0.01 liters and then 0.49 liters there. So now with the information of what each of the three parts mean and what it would mean to put 0.5 in any of the three spots, let's go through a sample problem. Jar A has 23% acid, jar B has 81% acid. The contents of both jars is poured into a bucket, creating 55 liters of a 36 acid solution. How full was jar B? Now there's two ways to do it, so I'm going to draw a line down the middle, and looks like this. First, I'll just take the percentages and write these on the concentration lines as decimals, both in this way and that way. Now, the final bucket at the bottom has 55 liters of stuff, so what I did is I placed the 55 here and in this version as well. But how full is jar A and how full is jar B? Here and here, we don't know, so I'm just going to stick an X and a Y and an X and a Y. That so far looks the same for both of these. I didn't want an X and an X because that's saying that both jars are full by the same amount, and we don't know that. That's an extra assumption that the problem doesn't let us do. But the amount of liquid from this jar and the amount of liquid from this jar should add together to be 55. So X plus Y equals 55. The same is true here because the diagram hasn't changed. And then here's where things will be a little different. Somebody is going to want to solve for X. Somebody's going to solve for Y. So over here, this is what solving for X looks like. Over here, somebody said, I'd like to subtract X on both sides and solve for Y. So in this version, when X is 55 minus Y, we're going to go up here and replace the X with 55 minus Y. And over here in this version, since somebody solved for Y, we're going to replace the Y that appears right here with 55 minus X. Now, we can apply this formula, right? That, actually, before applying the formula, let me point out that if you do 55 minus Y and add that to Y, that will be 55. Same deal here. If you do X plus 55 minus X, that simplifies to 55. So that's just to check the amount of liquid plus amount of liquid is amount of liquid. Same deal here, amount liquid plus amount liquid is amount liquid. Now though, we can apply the formula. As soon as you have two spots filled in for a jar, you can fill in the third spot. So if you've got amount liquid times concentration as a decimal, fill that in right there. So I did this in all the spots. Sorry for how this kind of spilled off screen right here, right? But this times this is that, 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 this times this is here. So I think you can see what should be there, and then this times this is that. And then finally what we do is, while the amount of acid in the bucket has been written here and in the other version, the amount of acid also is just how much acid is contributed here added to how much acid there. So I took this plus that and wrote it here, and in the other version I took this plus that and wrote it here. So even though it cut off there, you can see what it looks like here. The point is that for the bucket, the amount of acid is written two different looking ways. One way was this times this right there, and this way was this plus that here. Same deal over here. It was this times this written here, and the amount of acid down in this bucket was this here, plus sign right there, that, sorry for how it spilled, but it's written right there. So now what we do is, since the amount of acid for the bucket was written two different looking ways, I just set this equal to that. That's down here, or I set this equal to that, and that's down here. Now, these are both to the left of this bar and to the right are perfectly valid ways to do this. What I did is I went ahead on the next slide and just copied the diagram, the version that had x variables in it, and I just took the equation and went through solving. Now the value of X doesn't answer the question though, because it was how full is jar B, and jar B, the amount of liquid in here was 55 minus X. So if you do it this way, 55 minus the value of X is the number of liters of liquid that jar B had. If you go to the first diagram that I had, then this was the equation, and there are the steps for solving the equation, and the amount of, still, how full was jar B? Now it's just represented by the variable y itself. So the value of y, I just copy pasted here, that many liters of liquid, that's how full this is. So we just did this question up here two different ways, but I'm going to change the question slightly and do the following. 23%, 81%, the bucket being 36%, that's all the same. The difference is, in the question we just did, 55 liters was the amount of liquid, or the amount of solution for the bucket at the bottom, and now 55 is the amount of liquid for jar A. So how does that change things? Well, I copy pasted the question at the top of the next slide. First, let's just place the percentages as decimals in these spots, right? is not surprising that that hasn't changed. This 55 here goes in this spot, so we'll write that in. We don't know how much of jar B, that's the question, so I'll create a variable. I called it lowercase c. And now we still, like the previous slide where this plus that should be this, we can stick that here. It's just we didn't need to create an equation off to the side and remove one variable or whatever. That's one thing that's different, but 55 plus c is written right there. Now that 2 out of 3 spots are filled in, we can use the equation to fill in the other spots. Okay, this times this is this times this is this times this is this, and finally the amount of acid down in the bucket can be written another way. It's how much acid is contributed here plus how much acid is contributed there. Now the two different looking ways of the amount of acid for the bucket we set equal to each other, and I'll leave it to you to solve this equation. By the way, the value of C actually answers how full the jar was, right, in liters.